Hey, how you doing? So I've been playing around with the sequencer circuit and installed our analog circuitry. And as you just heard, we can now make chords and melodies. I wouldn't say it's melody that's in tune, but it's better than the sound effects we've been making so far. I also made a little kick drum circuit, just to give everything a bit of a sense of rhythm. But we'll cover how this works in a future video. As you can see, this whole thing is an even bigger mess than it was last time. Then add all the patch cables on top of it, and you get this. But how exactly have we gotten it to this point? And how does it work? Well, let's do the same thing as last time, and pull apart the analog circuitry, and build it back up again piece by piece. I also just wanted to give a quick shout out to Mum for knitting me this kick-ass jumper. We're starting to get into the depths of winter now, so I can't really get away with wearing just a t-shirt anymore. So this is what we were up to last time with the sequencer. At the moment, we basically have some fun flashing lights, but it doesn't actually make any sound. So this is where the analog elements of the sequencer will come in. But how exactly are we going to create these analog elements? If you remember at the start of my last video, I said we're going to create a hybrid between a Baby 8 and an MFOS 10-step sequencer. But why exactly are we going to do it this way? If we look at the schematic for a Baby 8 sequencer, if we ignore all this stuff down here and just focus on what's in the middle, then we can see we've got a 4017 chip, which is a 4022 in our case. But we can see that off the 10 connections, we first have a series of resistors and LEDs to give an indication of which step in the sequence we're on. And then we also have a series of potentiometers connected to a series of diodes, which is being used as our pitch CV. But when you look at the functionality for a Baby 8, it really doesn't do much at all. We have the lights and we have the pitch CV, which is cool, but there was so much more potential for different kinds of control with this circuit. So that's where the MFOS 10-step sequencer comes in. We can see looking at this part of the schematic that there was quite a lot going on. But what we basically have is a series of transistors being used to drive the LEDs. And then down here we can also see that there's a bit of a gate generator, which is relatively easy to understand once you dive into the schematic a little bit. And then we come to this part of the schematic where we can see how the pitch CV is generated, which is fairly easy to understand once you look at the circuit a bit more. But then we get to this part of the sequencer, and you look at this and you're like, what the hell is going on here? I absolutely love Ray's designs, but my god did he over-engineer them sometimes. Because this is just... what is going on? Like, there was so much information about Ray's logic and control for the sequencer that I was just like, nah, we'll just make our own. It's going to be a lot easier than trying to understand all of this. But combining the super simple aspects of the Baby 8 and the quite complicated aspects of the MFOS 10-step sequencer, I think it's possible to create a bit of a hybrid between the two, and just take the best elements of both of them. So how are we going to make the analog elements for our sequencer? Creating a hybrid between the Baby 8 and the MFOS 10-step. Well, what I've drawn here is just a 4022 chip again, with our step on-off switches. Now all the reset and control logic still applies, but obviously I'm not just going to be redrawing all this all over again. So you'll just have to imagine that all of this still exists on our analog circuit. And then when it comes to making the final design in KiCad, we'll just combine all of this into the one file. Now as you can see, I've also drawn a resistor, but I haven't actually given it a value. And this is for a good reason. When we look at the 10-step sequencer, we can see that we actually have a series of transistor drivers for the LEDs. Now what's the difference between using a transistor driver or just connecting an LED to a resistor? Well, for the most part, logic chips really don't deliver much current on their outputs. And because I'm using a bunch of blue LEDs, which require quite a lot of current to turn them on, what we can instead use is the transistor driver, which means that we can use a much smaller current to turn on the transistor, and then allow current to flow between its collector and emitter, turning on the LED. But looking at all this mess, it's not really obvious how this works at all. So let's redraw this into our diagram so it makes much more sense. So looking at our schematic now, I think this makes much more sense. On the output of each switch, we'll have a 47K resistor, which delivers a small amount of current to the base of the NPN transistor. So this small amount of current to the base of the NPN transistor then allows a larger current from the 12-volt rail to come through the collector and emitter, turning on the LED. So this means that the current driving the LED is separated from the outputs of the 4022 chip, which means that most of its current can be delivered to the analog elements being used to create the pitch CV. But since I have pretty limited real estate on these breadboards to wire in a bunch of transistors, we'll just leave the resistors and LEDs as they are. It still functions perfectly fine at the moment, But just remember, this isn't how it's going to be in the final design. So how exactly are we going to create the pitch CV? Well, if we look at Ray's design, we can see that he just has a series of potentiometers wired as voltage dividers, which are then connected together and go to a series of op-amps being used to create the pitch CV. But when I was playing around with this design, I actually found that each output was affecting the other one, rather than being entirely separate from one another, which isn't really good if you're trying to change the pitch on the first step and it's affecting all the other ones. So instead of doing it that way, I decided I'd go back to the Baby 8 and use a series of diodes instead. And the way that these are configured means that they essentially work as a giant OR gate. Because current can only flow one way through a diode, it means that the current coming through these lines isn't then coming back and up into one of the other ones. So on our diagram, what we also want is to have this line also connected to a 100k potentiometer, which means that we can adjust the potentiometer between the full output voltage or ground. When we wind the potentiometer towards ground, it means that we'll get a low frequency from our oscillator, and then when we wind it more towards the output, we'll then get a higher frequency tone from the oscillator. So coming out from the middle pin of these potentiometers, we then also want our series of signal diodes. Now technically at this point, we could actually connect a jack directly to the output of all of these diodes, because remember that we're repeating all of this circuitry 8 times, which will work absolutely fine. But I think there's way more that we can actually do with the pitch CV. So this is where Ray's design comes back in again. Because he's using a series of resistors, it's then going to an inverting voltage summer, which is then being re-inverted again to create the non-inverted version, and it just always a bit complicated. So let's just ignore this left half of the diagram, and instead let's just focus on the right half over here. Now these two op-amps are creating a glide, slide, slew, or portamento circuit, which basically means that each step in the output can sort of glide between one another. Rather than just abruptly stepping between each of them, it kind of smooths out the pitch CV a little bit. So with this circuit, we can basically adjust how much of the voltage is being dropped directly onto the non-inverting input of our op-amp, or how much is being dropped through the capacitor. So by adjusting this rate, we can actually change how much of a glide we have between each note in the sequence. But this will be much more obvious once we wire it into the circuit and plug it into the synth. But before that, let's quickly draw it into our diagram so it's a little less messy than all this. Alright, so I've now drawn out our glide, slide, slew, portamento circuit, which is being used as our pitch CV output. And also note that I've drawn a 100k resistor at the output of each of the diodes, just to maintain that they actually work as an OR gate. But this connection from the string of diodes is then going into our portamento circuit and being used as our pitch CV output. So depending on which way the potentiometer was wound, we'll hear the pitch on each of the outputs either abruptly jump between one or another, or softly slide between each of the different pitches. So now that we have an idea of how the pitch CV is going to work, let's bust out another breadboard and stun build our analog circuitry. Now I've got a second breadboard here, wired up to our first one through the power, and I've also got some rails on the side just to create our virtual ground points. But I've also got this big long string of 12 potentiometers. These first 4 up the top were being used for the first 4 steps of the second sequencer, and these 8 potentiometers were being used for all 8 outputs of our first sequencer. And you can see that I've connected each bottom leg together, which should actually be connected into ground. Rather than wiring these 4 ones back up to the second sequencer again, we'll just focus on these bottom ones down here, which means I can actually take them out. And from the middle pin of each of these potentiometers, we then want our signal diodes to be connected. Alright, so I now have 8 signal diodes connected to the middle pins of each of our potentiometers. And then the outputs of these diodes are all connected together and then wired to a 100k resistor, which is going to ground. But the next connection we need to make is from the top of the pots to each output of our 4022 chip. Alright, so I now have our pots connected to the steps on the sequencer, and technically I can now plug in a jack to the bottom connection down here so we could use our pitch CV. But let's just keep going and add an op-amp to the breadboard so we can create our portamento circuit. Alright, so I now have our entire pitch CV circuitry installed and interfaced into the sequencer. So now let's go and plug this into the synth and hear how it sounds and works. Alright, so I now have the sequencer connected up to the synth. I first have one of our oscillators on the TTO going into the filter and then into the mixer. I then have the pitch out of the sequencer going into the LFO input on the TTO. Then up in the corner here, I have the crazy clock connected so that we can use its manual mode to pulse through each step in the sequence. So if I bring our oscillator in, we can hear that we have a low frequency tone as the pot is wound towards ground. But as I increase the pot more and more towards the step output, we can hear that the tone from the TTO increases in pitch. And this tone is also completely unaffected by any of the other outputs. If I adjust any of our other pots, they won't affect the step we're currently on. But by dialing in the pitch that we want for each step in the sequence, you can see how we're now able to create a melody. So let's try and make something. Alright, so I've got a little sequence dialed in. Let's flick the crazy clock back to auto mode and hear how it sounds. And you can also hear that as I adjust our portamento pot, we can hear how each note in the sequence slides into one another, rather than abruptly stepping between each other. But as I turn it up further and further, we end up sliding all the notes together so much that it just sounds like one big note wavering in pitch. Now you can hear that as I adjust the cutoff on the filter, we're able to really change the quality or timbre of our melody. But what if we want to use a CV to adjust the cutoff, rather than my hand doing all the work? Well, let's plug in the envelope generator and play around with the attack and decay parameters to shape the cutoff control voltage for our filter. Now you can hear that as I adjust the attack and decay, we can get some pretty funky sounds from our melody and filter. But the problem with the envelope generator in repeat mode is that it isn't really in synchronization with the clock or the sequence. It's just flapping about in the breeze doing its own thing. But this is why I included the gate input for the envelope generator, so that we can use the signal derived from our sequence to affect the attack and decay controls, therefore putting everything back in sync with one another. But how are we going to create this gate signal from the sequencer? Well, let's go back to the breadboard zone and add in the gate functionality. Alright, so when we look at the 10-step sequencer, we can see that we have a series of diodes and switches coming out from the emitters of the transistors. The common connection of all these diodes and switches is then going into a comparator, which is then coming up into this little janky arrangement, which is connected up to the logic and control. But rather than trying to understand how all of this works connected up to this point, we'll just put in a series of diodes and switches into our sequencer and connect it directly to a comparator. And the output from this comparator is what is being used to create our gate signal. So for each step in the sequence, we can selectively choose whether we want to have a gate or not. When I was originally playing around with this design, I found that having the diodes connected to the emitters of the transistors didn't actually produce the results that I wanted. And I found that I actually got a better result just having the diodes connected directly to the outputs of the chip. But first, let's draw all this into our diagram so it makes much more sense than all this. And then we can put the circuitry into the breadboard and really get an idea of how the gate signal will work. Alright, so I've now redrawn our schematic to include our gate circuitry. Now the other thing that I'll point out is that I've created the virtual ground circuitry over here. So we have two 4.7k resistors going between power and ground to create our 6V virtual ground point. And this is where all of our outputs and comparator is connected to. So anywhere there's a dotted virtual ground point is where it'll be connected up to here. Now as you can see, what we'll have is 8 signal diodes and switches, with the voltage being dropped onto the 100k resistor, and then also coming into our comparator. So this comparator will compare the voltage coming into its input on the non-inverting terminal to the virtual ground point on its inverting terminal. So if the voltage on the non-inverting terminal is above 6 volts, then we'll produce a gate on the output, and we'll also light up this LED here. But if the voltage on the non-inverting terminal is less than the 6 volts on the inverting terminal, then no gate will be produced, and we'll see the LED turn off. So for each step, we can selectively choose whether we want a gate or not. We can then further process this gate signal and turn it into a trigger by using a simple RC circuit with a 0.1 UF capacitor and a 20k resistor, and then another signal diode just to maintain that only the positive voltage comes through. Now this selective gate on-off capability will also be separate from the step on-off capability, meaning that for each step in the sequence, we can choose whether we want the step on or off or the gate on or off, which will produce some interesting results and sounds. This trigger output is what I was using to trigger our kick drum to give everything in the patch at the start a sense of rhythm. So now that we have an idea of how the gate circuitry is going to work, let's put it into the breadboard and see it in action. Alright, so I now have our gate circuitry installed. I have all the connections coming over from the 4022 chip into the string of diodes, which then have all their cathodes connected together and coming over into the comparator. But you can see at the moment that our gate LED is constantly held on, as we're producing a gate on every single step in our sequence. But if I now remove a couple of steps, we'll see that the gate signal now goes on and off, depending on which step in the sequence we've actually selected. But watching some LEDs flash isn't really too exciting. So let's go and interface this with the synth again, and hear how we can use this gate signal to affect the attack and decay parameters on our envelope generator, therefore keeping the modulation on the filter in synchronization with our sequence. Alright, so now I have the sequencer interface back with the synth again. So if I unmute our mixer and play around with the envelope generator, we can hear that we get our funky effects with the envelope generator set to repeat mode, but we want it to be in synchronization with our sequence. So we have the gate input signal connected to our gate output from the sequence. So if I now flick the envelope generator back to manual mode, we can now hear that the envelope that is being generated is now back in synchronization with our sequence. But adjusting the attack and decay doesn't do anything, because we're constantly producing a gate from our sequence. But if I remove the gate from a couple of steps, and adjust the attack and decay, we can now get our funky effects from the envelope, but it's in synchronization with the sequence. And if I flick the crazy clock back to manual mode, we can hear how the gate adjusts the attack and decay for the envelope, depending on which step we are in the sequence and whether the gate is produced or not. So you can see that when a gate is produced, it affects the attack cycle on our envelope and therefore the modulation on the filter. But then when no gate is produced, it affects the decay parameter of our envelope generator and therefore the modulation on the filter. and we can also remove certain steps from the sequence. So as you can hear, we can get all kinds of different crazy sounds and modulation from the sequencer, the filter, and the envelope generator. This is going to just be an insane amount of fun once I convert all of this into a PCB and a final module, and then place it into the gap down here. So that's it for today's video. It's absolutely awesome finally hearing the synth starting to make some melody, but there's still a few things left I want to explore before we fully convert this to a PCB, such as using another 7-segment display to count along with each step in the sequence, and also working out the trigger arrangement for some drum modules. If you decide to have a go at building this sequencer circuit, let me know how you go in the comments down below. Just remember to watch part 1 of this episode so you understand how the control logic works, which you can find up here. But until next time, I will see you later.